Two atomic nuclei were moving toward each other far too slowly to fuse. Their positive electrical charges should have forced them apart long before the strong nuclear force could pull them together. According to the usual calculation, the probability of a reaction was almost unimaginably small. Then researchers placed those nuclei inside metal. The result did not resemble an ordinary plasma experiment. There was no magnetic chamber holding gas hotter than the center of the sun. Instead, deuterium atoms were packed into palladium and titanium foils while a low-energy ion beam struck the material. Below an energy of about 2.5 kiloelectronvolts, the expected fusion rate should have collapsed exponentially. Instead, the researchers observed an unexpected plateau. Compared with calculations for unshielded nuclei, the measured reaction yield was enhanced by more than 10 to the power of 18. That is a factor of more than 1 quintillion. The experiment does not demonstrate cold fusion, and the reaction rate remains far too low to generate useful energy. But it reveals something important. The material surrounding atomic nuclei can radically alter how easily they undergo fusion. The central question is no longer only how hot, fast, or compressed the fuel becomes. It is also what kind of material holds the fuel while the reaction occurs. Fusion normally begins with a formidable obstacle known as the Coulomb barrier. Deuterium is a heavy isotope of hydrogen. Its nucleus contains one proton and one neutron. When two deuterium nuclei approach each other, their positively charged protons repel. The strong nuclear force can bind them together, but it acts only across an extremely short distance. The nuclei must first get close enough for that force to take control. In stars, enormous temperature and pressure give nuclei enough energy to collide frequently. Even then, most encounters do not result in fusion. The nuclei usually repel and separate. Quantum mechanics provides another route. A nucleus behaves partly like a wave rather than a perfectly solid ball. That wave has a small probability of passing through the electrical barrier instead of climbing over it. This is quantum tunneling. The lower the nuclei's energy becomes, the less likely tunneling is. Fusion probability therefore falls extremely rapidly as the particles slow down. At the energies used in the new experiment, standard bare nucleus calculations predicted that deuterium fusion should become nearly undetectable. But nuclei embedded inside a solid are not bare. They are surrounded by electrons, crystal atoms, defects, and other hydrogen nuclei. Those surroundings change the electrical environment through which an incoming ion must travel. Electrons are negatively charged. Their presence can partially shield the positive charge of a deuterium nucleus. From the perspective of an approaching nucleus, the repulsive barrier becomes slightly lower or thinner. Even a modest change can have a dramatic effect because tunneling probability depends exponentially on the barrier. Imagine trying to cross a mountain through a tunnel. Shortening the tunnel by only a small fraction may not sound important. But if the chance of completing the journey decreases exponentially with every meter, a small reduction can multiply the success rate enormously. Scientists call this effect electron screening. Electron screening in metals has been studied before, but the behavior of fusion at extremely low energies remained poorly constrained. Experiments become increasingly difficult as the reaction rate falls. Small uncertainties in hydrogen concentration, contamination, beam energy, or detector efficiency can dominate the result. Researchers from the University of California, Davis, and Lawrence Berkeley National Laboratory designed a dual-chamber system to control several of those variables. In one chamber, they loaded metal foils with deuterium through an electrochemical process. Palladium and titanium can absorb large quantities of hydrogen isotopes into spaces within their crystal lattices. The loaded sample then moved into a second chamber, where a beam of deuterium ions struck it. The incoming ions collided with deuterium already stored inside the metal. Some collisions produced fusion reactions that released neutrons. By measuring those neutrons, the researchers could estimate how often fusion occurred. The arrangement allowed them to change both the ion energy and the amount of deuterium inside the target. This was essential because a metal cannot enhance fusion if it contains too little fuel. At relatively high beam energies, the measured reaction rates followed more familiar expectations. As the energy decreased, however, the behavior changed. Below roughly 2.5 kiloelectronvolts, the fusion yield stopped falling as quickly as standard models predicted. It entered a plateau-like regime. The effect appeared in both palladium hydride and titanium hydride, although the details depended on the material and how heavily it had been loaded with deuterium. This suggests that electron screening alone may not explain the entire result. A solid is not a smooth container filled with evenly distributed particles. Its atoms form a lattice, and that lattice contains grain boundaries, vacancies, dislocations, and damaged regions. As the ion beam enters the target, it can create additional defects. Deuterium atoms may migrate toward those disturbed regions, forming local concentrations much higher than the average value across the foil. The incoming ion may therefore encounter small hydrogen-rich environments where fusion is more likely. The material can influence the reaction in several ways at once. Its electrons modify the electrical barrier. Its crystal structure controls where deuterium accumulates. Its defects change as the beam continues striking it. Its chemical state affects how quickly hydrogen enters or escapes. The target is not merely holding the reaction. It is actively shaping the conditions under which the nuclei meet. This is why the researchers describe the phenomenon as materials-driven fusion. The phrase does not mean that a metal foil is producing abundant energy on its own. It means that the electronic and structural properties of the material become important variables in nuclear reaction physics. Historically, fusion research has focused mainly on controlling the fuel itself. Magnetic confinement systems attempt to hold extremely hot plasma away from reactor walls. Inertial confinement experiments compress tiny fuel capsules with lasers. Accelerator experiments fire ions into targets at carefully selected energies. The surrounding material is often treated as a component that must survive heat, radiation, and mechanical stress. The new work suggests another possibility. In some low-energy regimes, materials might be deliberately designed to influence the reaction rather than simply endure it. Researchers could adjust electron density, crystal structure, hydrogen mobility, and defect concentration. They might compare alloys, layered materials, or nanostructures to determine which environments produce the strongest and most reproducible enhancement. This is conceptually similar to catalysis in chemistry. A chemical catalyst changes the pathway of a reaction without becoming the final product. It does not violate energy conservation or create energy from nothing. It changes how difficult it is for reactants to reach the necessary configuration. A fusion-supporting material would not be a conventional catalyst because nuclear and chemical reactions operate through different forces. But the engineering philosophy is similar. Design the environment around the reactants so the desired event becomes more probable. That possibility must be kept in perspective. An enhancement of 10 to the power of 18 sounds as though the researchers have solved fusion energy. They have not. The comparison begins with an almost vanishingly small theoretical rate. Multiplying an extremely tiny number by a quintillion can still produce a result that is small in absolute terms. The reported reactions consumed more energy than they released. The ion beam, electrochemical loading equipment, vacuum system, and detectors all required external power. Nothing in the study indicates a self-sustaining reaction or a practical electricity source. The work also differs from controversial cold fusion claims. Those claims generally involve reports of unexpectedly large heat production or nuclear products during electrochemical experiments near room temperature. Many could not be reliably reproduced, and no accepted mechanism explained the alleged energy. In the new experiment, researchers supplied deuterium ions with controlled energies, detected neutrons from known fusion channels, and measured how the yield changed across different conditions. The goal was not to claim excess energy. It was to study how a solid environment modifies a measurable nuclear reaction. Reproducibility will still be critical. Independent laboratories need to test the effect with different equipment. Researchers must separate electron screening from changes in local deuterium concentration and beam-induced damage. The plateau may involve several mechanisms operating together. Understanding their relative importance will require direct measurements of the target while the reaction is occurring. Scientists may use microscopy, spectroscopy, and computer simulations to map where deuterium accumulates inside the lattice. They may compare crystalline samples with amorphous materials, damaged regions with undamaged ones, and different metals with similar hydrogen concentrations. If the enhancement can be predicted and controlled, it could improve compact neutron sources. Neutrons are used to examine materials, produce some medical isotopes, test radiation effects, and identify chemical compositions. Many neutron sources rely on reactors or relatively large accelerator systems. A material that increases fusion yield at lower ion energies could potentially make some neutron-producing devices smaller or more efficient. That application is closer to the scale of the present work than a power plant. The experiment may also help nuclear astrophysics. Scientists study low-energy fusion reactions to understand what happens inside stars. Laboratory measurements usually occur at higher energies because the natural stellar reaction rates are difficult to detect. Electron screening inside laboratory targets can distort those measurements. Better models of how solids alter fusion may help researchers separate the intrinsic nuclear reaction from the influence of the experimental material. The deeper significance is that nuclear reactions are not always isolated events between two particles. At very low energies, the surrounding electrons and atoms can become part of the reaction environment. A nucleus approaching through a metal lattice experiences a different path from one moving through empty space. The nuclear force itself has not changed. The material changes the probability that the nuclei can get close enough to feel it. Inside the palladium and titanium foils, deuterium atoms occupied hidden spaces between metal atoms. Electrons soften part of their mutual repulsion. Defects may have gathered the fuel into concentrated regions. Incoming ions repeatedly tested the barrier. Most still failed, but far more succeeded than the bare nucleus model predicted. The experiment did not create a miniature sun inside a sheet of metal. It revealed that the road toward fusion can be reshaped before the nuclei ever meet. Future fusion systems may still require immense temperature, pressure, and engineering. But this research adds another design tool to the problem, not only controlling the fuel but engineering the material world immediately around it.